So if you recall, last time we had talked about how to terminate a stream, and I mentioned that there's various ways to terminate a stream. You can have a terminal operation that has no return value, such as for each or for each ordered. We also talked about how to do a reduction operation using the reduce terminal method, which takes the contents of the stream and returns a single primitive value. And then we'd also talked about collect, and collect basically takes the elements of the stream, collects them together, and returns some kind of aggregate collection. And so what we're going to do now is we're going to talk about how to actually implement a non-concurrent collector for sequential stream. And you'll see the non-concurrent collector is a little bit odd the way it's phrased, because it actually can work for a parallel stream. And I will mention that briefly at the moment, but this focus is going to be on sequential streams. Later, we'll come back and talk about this in the context of parallel streams. So just to reiterate what I said before, remember a collector, like a collector that collects things into a list, is used to terminate a stream. And remember that collect does two things. First, it triggers all the intermediate operations to run, so they do their thing. And then they generate results, they generate elements in the stream, and then the collector, which is the thing shown in red, the object returned by the toList factory method, that collector will then accumulate all those elements and return some kind of collection. In this case, it was a list of strings, but it could be a set or a map or whatever. It all depends what you tell it to do. Collector is an interface you can read about here, whose implementations can accumulate the input elements in a stream into a so-called mutable result container. So that's essentially what a collector does. And we'll see that there's a bunch of parameters that you pass it, and there's a bunch of methods that a collector provides. Collector implementations, in other words, the things that either you write if you want a custom collector, or things that you get out of the box if you're using what comes with Java in the Java class library, they can either be concurrent or non-concurrent. And I'll explain what that means in a second. And the way that you can designate whether they're concurrent or non-concurrent is by one of the characteristics that you can designate through a characteristics factory method. And you'll see that there are three characteristics. So we'll talk briefly about what these characteristics are. The main one I want to emphasize here is concurrent, but we'll also talk about the other ones as well. The distinction between being a concurrent collector or a non-concurrent collector only matters for parallel streams. If you have a sequential stream, first of all, you might as well use a non-concurrent collector because there's no concurrency going on. You could use a concurrent collector, but it would be totally pointless and overkill for reasons we'll talk about in a second. If you have a parallel stream, then things actually matter. There's a difference in the way that the two approaches work. But oddly enough, they both work fine for parallel streams, just one is optimized in certain ways. As I mentioned before, we're just going to focus on non-concurrent collectors for sequential streams, and we'll talk about concurrent collectors and non-concurrent collectors for parallel streams later, probably in a week or so. So you can think of a collector, or a non-concurrent collector in this case, for a sequential stream is simply a way to accumulate elements into a mutable result container. So remember, you've got a stream of elements, values, data, objects, whatever you want to call them. And the goal of a collector is to put them someplace. A collector is essentially the inverse of a splitterator. So if you recall, what does a splitterator do? A splitterator takes a single input source, like some kind of an array or a list or a file or something, and it splits it into a stream of elements. So after we split things up, we have a stream of input, which is then processed. The collector takes the results of all the processing and joins it all back together again into a single result. So that's why I said it's kind of an inverse, right? It kind of, you take it and it puts it back into a single common source, or a single common sink, not a source, a sink. There are three generic types that are defined in the collector interface. And as we'll see, they're using Java generics. Hopefully everybody remembers what Java generics are. Java generics are a little bit like templates in C++, but not nearly as powerful, not nearly as cool. But they do the job. They allow you to parameterize classes based on type. One of the types, T, one of the parameters, T, stands for the type of objects that are actually in the stream. That could be a stream of integers, it could be a stream of strings, it could be a stream of search results, all kinds of things you could have a stream of. So that's just the type of the element in the stream. The next type, A, is the type of accumulator object that's used for the collection, or for collection. It's intended to be mutable. All that means is that you can update it. So we might have a list of T, which would be implemented as an array list or a linked list or something else. And then the final third type is R, and you might guess R stands for result. So it's whatever the collector is going to return when it's called. And you might have, for example, a list of T might be the thing that you give back as the result type. So those are the three type parameters. And you guys will get a chance to implement a collector for your array class that you wrote when we do assignment number 3. So assignment number 3 is where we get a chance to actually do all this stuff. So we'll talk about it now, and then when you have that assignment, you can come back and rewatch the video. So there's also 5 methods that are defined as part of the collector interface, and we're going to focus here on the non-concurrent collector semantics. There's also concurrent collector semantics, which we'll talk about later. The first method, which is what sets whether you're concurrent or not, is called characteristics. And as you can see, it returns a set. The characteristics method returns a set of characteristics, which, as we'll see, is essentially an enumerated type. And this characteristics enumerated type, or this set, gives you additional information. It's basically metadata that describes what kind of a collector you have created. So one of the characteristics you might choose to set is called unordered. And that means that the collector is not obliged to preserve in counter order. In counter order is just a fancy name for the order in which the input appeared in the original source for the stream. So let's assume, for sake of argument, we had a list. So the encounter order would just be the order the elements were in the set, or sorry, in the list to begin with, from left to right. So if you say unordered, then there's no obligation to preserve in counter order. The collector can reorder things. So just let's assume, for sake of argument, that the original thing was ordered, like from low to high. If you have unordered, then it can give the results back in any order, as long as they're correct, as long as it doesn't drop things or duplicate them and stuff like that. A collector may preserve in counter order, even if it's an unordered collector, if there's no additional overhead in keeping it in order, it doesn't hurt anything. So unordered just means let the system decide how to optimize. Now, it turns out this ordered versus unordered characteristic really only matters for parallel streams. And I'll talk about that more later. And the reason for that is that if you want the collector to order something, then there's extra work required to make sure that after everything runs in parallel, the results are presented in counter order, because you have to basically store everything and then make sure that they go back in the right order. Conversely, if you have an unordered collector and a parallel stream, then whatever order they happen to arrive in first as they run in parallel, that's perfectly okay. So if you don't care about in counter order, collector should be unordered, because it provides the opportunity for optimization by the streams framework in the case where you're using a parallel stream. So the next characteristic we'll talk about is called identity finish. And the way it works is sometimes the accumulator and the combiner, when used by the streams framework, will end up putting all the elements in the stream that are being collected by the collector in such a way that there's no need to have any additional finisher method to turn it into a final result. And if that's the case, you can simply set the identity finish characteristic, and that's an indication to the streams framework that the finisher method is the identity function. So it can essentially be a no-op and just return null. There are other cases where that's not the situation, and you actually have to do something in the finisher method. And I'll talk more about that in another context later. We'll talk later when we talk about parallel streams and talk about computable futures, how there often is something else you have to do. Yes? It's the identity function. So in other words, it's just, what that means is that the way the accumulator ended up after the final element was placed into it by the collector, by the accumulate method or the combiner method, that will end up just being in the final result. So it's the identity function. It'll just return what the current item is, the current accumulator is. Oh, sorry, was your question, is it identity finish? Yes, it's identity finish, not identify finish. The next element, which is really the whole point I was focusing on here, is concurrent. And the concurrent characteristic means that the accumulator method is called concurrently on the result container, or could be called concurrently. And what that means is there could actually be multiple threads of control that are all simultaneously accumulating elements into the mutable result container. So the implication of this is if the concurrent flag is set, if the concurrent characteristic is set, then the implementer of this has to make sure that the mutable result container is properly synchronized. So it might have to use a concurrent hash map, or it might have to use a concurrent list or something like that. If you, as we'll see, we're not focusing on the concurrent model here. We're just focusing on the non-concurrent version. So concurrent should not be set, which means we don't have to have any synchronization in place at all. The way in which these characteristics are either set or not set is by the characteristics method. And here's one example of how you could set any or all of these flags. You could simply use enum set of, and then you could list the characteristics that you want to have included, which could include nothing. And so this basically says enum set of. In this case, we're giving all three of them. That would be somewhat unusual, but it's possible. And then we're making it returned as a so-called unmodifiable set. And an unmodifiable set simply means that once this set is set, the elements of the set cannot be unset. Kind of a mouthful, but that's what it means. Okay, so that's characteristics, and that sets the semantics. For the discussion we're having here, let's assume that concurrent is not set. Supplier is a factory method that returns a constructor reference or something else that makes the empty mutable result container. So here's a simple example of supplier. In this case, this one implementation of supplier could simply return a constructor reference to make a new array list, which will of course be what's implementing the list interface. You could also say linked list or something else. But the point is that supplier gives you back a supplier which will make something when it's called. If you remember supplier, remember we talked about the supplier interface, it has a get method, and when you call get, it invokes whatever it's implemented by. In this case, it would be a constructor reference for array list. Accumulator is the thing that takes the next element in the stream and then adds it to the mutable result container. So it's going to accumulate the results. This is what the method looks like. Accumulator returns, basically it's a factory method that returns a by consumer that when called will add the next element, in this case an integer perhaps, to whatever the container is, which in this case is a list. And in this case, you can see we're just saying return list : add. So we're saying go ahead and return a method reference to the add method, which is what's used to go ahead and take the next element in the stream and add it to the mutable result container, which in this particular example is a list. You can see up here, this is the part in red up here is the actual parameters that are defined. So you can see it takes an accumulator, which in our case is list, and a type t, which in our case is integer, and it returns a by consumer, and list : add is something that will fit that particular type. So it's a by consumer. A non-concurrent collector needs no synchronization for its accumulator. So this works perfectly fine. The combiner is a binary operator that merges two result containers together. So you could see here, if we needed to have a combiner, and a combiner is not needed for a sequential stream, but it is needed for a parallel stream, even if it's a non-concurrent collector, then what the combiner does is it takes two lists and it adds another to one. And it's important to note a couple things. First of all, it's important to note that this is ordered. So we put the first one first, followed by the contents of the second one. So that'll keep things ordered. That'll preserve in counter order. So that's what happens by making sure that another goes at the end of one. So add all, just sticks it at the end. Second thing to note is, once again, for a sequential stream, and even for a parallel stream for that matter, there is no need to have any synchronization here, because this is always done in a single thread of control. And then we return the merged list. So that's combiner. And then the fifth method, which is the last one, is called finisher, and that returns a function that converts the result container to the final result type. So for something like this, which, once you've accumulated everything by adding things to the list, you're done, then we can simply have the function return identity. So it just says return whatever you currently have. So it won't make any changes to stuff. And in fact, if we set the identity finish, and now I've correctly spelled it right, the identity finish characteristic, then we don't even have to say return function identity. We can just say return null. It can be much more interesting. So we'll take a look later in the course, probably in several weeks, when we talk about completable futures. And there's a really interesting example there called a futures collector. And that will actually return a future to a bunch of stuff. So it's wildly different from what the actual accumulator has been accumulating. The elements in that case would be something else, and it'll return a single future to all of them. So you can have much more interesting implementations of finisher, but for a lot of the simple data types, it's not necessary. Okay, so it's often the case in Java, especially older versions of Java, and even in newer versions of Java, they've continued this pattern, if you will, this idiom. They typically will have a so-called utility class that just has the name of the interface or whatever with an S at the end, right? So a good example would be the executor framework. There's an executor class, and then there's an executors, so there's an executor interface, and there's an executors, plural, class that has factory methods that make various kinds of executor implementations. So too is the case with collector. So there's the collector interface, and then there's the collectors class, which is a so-called utility class. And a utility class is simply a class that has no non-static fields, has only a private constructor, or has a private constructor, and only has static methods. So the whole purpose of a utility class is to be used to have factory methods that can, or helper methods that can make stuff typically, or do something, but it actually contains no state. So collectors is one of those kinds of things. It's a utility class, and it contains factory methods that create the collectors for common collection types like list or set or map and so on, and the appropriate implementations of those things. So here's an example where we have collectors, the class collectors, and it has a toList method, which you've seen many times before now. And toList is a factory method that returns a collector. You can see it returns collector here. Static, it returns collector. And what it does is it goes ahead and makes a new instance of something called collector impl. We'll look at collector impl in a second. And collector impl takes a bunch of parameters. One of the parameters it takes is the factory method to make a new array list. So it's a constructor reference. The second thing it does is it has an add method that adds and accumulates the next element in the stream into that array list. Then it writes out a little lambda expression that basically combines things. And then it also has this static final field called cur ID, which stands for, or ch ID, which stands for characteristic identity finish, which means there is no need for a finisher method. Yes, sir?
Did you say that it only has private constructors, so it can only be created internally, or have?
So, yeah, great question. So a utility class in Java, I mean, this is true of any OO language, but in Java for sure, it typically, a utility class has only static methods, no non-static fields, because there's only static methods, and it'll typically have a private constructor. The reason is you don't want to allow people to make instances of it. So it's really just a place to group together a bunch of functions. If Java was C++, which it's not, but if it were, in C++ you can have essentially, let's see, a namespace that would have a bunch of functions defined in it. So you can think of a utility class in Java as kind of like a C++ namespace with a bunch of functions defined in it that really don't have any fields that are non-static. So that's basically what a utility class is. It's a pattern or an idiom used commonly in Java. So this is an example of how we can have a method called toList, which comes out of the standard Java library, which makes a collector that has these various parameters set. Well, that sort of raises the question, what is collector impl? So collector impl is a simple class that's used to create collectors. And what's interesting about this is that collector impl is actually private. So it's only used internally by the Java collectors utility class. And so collectors essentially contains within it a private collector impl class. You can see it's got all these fields that correspond to the supplier, accumulator, finisher, combiner, and so on. And then it's got the methods we just talked about. And this collector impl implementation class implements the collector interface. And here's kind of how it's typically used. So here we have the collector of method. All right, so this is kind of funky. Collector.of is a public factory method. So that's something that you can call. You can't access, as a normal Java programmer, you can't access collector impl. You can't, because it's private. But you can access the of method. And if you recall in Java, especially Java 8, lots of things are made by of. So of is a factory method that makes stuff. So here we have the of method. As you can see, you pass it in a bunch of different functional interfaces, supplier, by consumer, binary operator, characteristics, and so on. And what it does internally is it says, hey, make a new collector impl, which we just sort of saw here. And so I kind of saw it there. It says, make a new collector impl that takes each of these parameters and bundles them up into the appropriate fields of the collector impl, which in turn will then be used to access the supplier, the accumulator, the combiner, the chars, and so on. So this is how you as an end user can create a collector very easily just by passing in lambda expressions or method references. And here's a simple example of this. So if we've been talking about search results in my examples I've shown you so far, the example programs I've shown you so far, we had this search results class. And one of the things the search results class does is it knows how to format its results. So when you look up words, like if you're looking up the lyrics to the Do Re Mi song from The Sound of Music, the search results thing will say, for word re, or re rather, here is the place where all the mentions of the word re occur. Here's where all the mentions of the word ti occur. Here's where the mentions of all the word la occur, and so on. And you can see how this is kind of nicely formatted. So each index is separated by a vertical bar. How does that get formatted, you ask? Well, the way it gets formatted is if you were to take a look in the search results class itself, you would find there's a toString method. ToString is a common Java method that's used to take whatever the data structure is and turn it into a string representation of the data structure's state. So what we do here is we take the list of indices, we turn it into a stream. So now we have a stream of indices, basically numbers, like these numbers here. And then we collect those things together. And over here we use collector.of, which is this factory method, and we give it several lambda expressions and method references. So we make a new string joiner. This is the factory method that's going to be used as the supplier. So it's this guy here, or this guy here. And string joiner is just a helper class that you can give it what you want to put between two strings. So when the strings are concatenated together, it'll put the separator there. And so we just tell it to use the vertical bar separator. Here's the accumulator. So this takes a string joiner and a new element we want to join in the string. and it goes ahead and adds that string to the string joiner. And of course, under the hood, it keeps track of the vertical bar and puts it in between that. We have this thing called merge, which would merge strings together if we need to. We don't need to do it in this case because it's essentially a sequential non-concurrent collector. And then the final thing, the finisher method here, takes a string joiner and converts it into a string. So you can end up getting a string, which could then be printed out just like any other string could be printed out. So this is just a good example of using collector.of to make a very simple collector on the fly. Yes, Allison? Where did the brackets come from? Oh, if you were to look at, so this is making the string part, and then there's a piece of code that is called, elsewhere that would have everything in between the brackets. So this is just showing everything in between the brackets. I'm eliminating some of the code. If you were to actually go and look in this search results.java file, you'd see there's a method called print, and print will say word, substitute the word, match the index, open square bracket, and then it'll say toString, get all the guts, and then it'll put a close square bracket at right-hand side, close square bracket at the end. Yes? Great question. So the question is, do you always have to use the of method in order to make yourself custom collectors? Absolutely not. There's other ways to make them. This particular factory method, the of factory method, which I show you here, is really particularly good if you can easily express the various methods that are needed to make a custom collector as either pithy lambda expressions or method references. If there's something more complicated, then you may actually want to go ahead and define your own class that will implement the collector interface. So there's two ways to do it. If it's a very simple thing where it's like this, where these are sort of all just kind of one-liners or method references, use of. If it's more complicated, and you've got to write like a big chunk of code, and we'll see some examples of that later, then you do not probably want to do that because it would just get unwieldy, and you'd have to make a big mess every time. So this is particularly good if you have very short things, but if you're going to want to reuse something, you just want to make an instance of it. This works well if you're only using of works well if you have very simple one-liners and you're only going to use them once. If you're going to do this multiple times, then it gets tedious to keep rewriting this code over and over again. So in that case, you're better off implementing that interface and defining your own class, and then making an instance of that class and using it various places. The way that toList works, for example. So just to make that point really clear, here is toList, right? toList is something that was common enough that it made sense to have a factory method in a class, and we're going to kind of abstract away this implementation detail. You could, of course, use collector.of. You could say collector.of. Every time you wanted to accumulate something into a list, you could say collector.of and then write code like this every time. But of course, very quickly you'd go out of your mind because it would be tedious and error prone. So it's much better to stash it away either in a factory method using something like collector impl, or actually implementing your own subclass that implements the collector interface. But yeah, that's a great question. I've only kind of scratched the surface of custom collectors. If you really want to learn even more about this, we talked a bit about it, but if you want to learn even more about it, there's a video here by a colleague of mine named Angelica Longer, and she is an expert on many different things. One of them is Java, and so she has about a couple hour, I guess it's an hour-long tutorial that talks about custom collectors in great, great detail, and she shows some really cool examples of how you could use them for interesting things. We will talk later about other kinds of stuff related to custom collectors, and I'll show you more interesting examples too. Okay, so that's the end of the Java Streams overview. In fact, that's the end of the overview of Java Streams, sequential streams altogether.